So we left off where we had derived the Euler equations, and I've written them here just to remind you that these are the torques that we observe, which are expressed along the three principal axes of the body. So these arise from the applied external forces to the system, and they're written in terms of the principal axis moments and the angular velocities about those principal axes. So we're going to begin with these Euler equations and then analyze some rather simplified situations. So, as I said previously, normally, because of the complicated nature of these equations, they're coupled nonlinear equations, they have to be solved numerically. But we'll go through an example that reveals some rather interesting physics with just a few simplifications. So we are going to assume a torque-free motion. So this would be for just a freely rotating body, no external forces on it, that induce torques, and that's the key thing. So for example, the throwing of a frisbee or a football, yes, there's an external force of gravity that acts through the center of mass, but to a high degree of accuracy, there's no external torques on the system. So what that immediately allows us to do is set the left-hand side to 0. And the next assumption we're going to make is we're going to assume a cylindrical symmetry. And with that cylindrical symmetry, we'll take two of the moments and set them equal to each other. So we'll just assume that I1 and I2 are equal. So this is what would apply to the frisbee or the American football. So we'll rewrite these equations under these assumptions. So now I have 0, I1, omega 1 dot. And for I2, I'm always just going to use the value for I1. So this is then I3 minus I1, omega 2, omega 3. And then about the next axis, we have 0. That's I1 omega 2 dot plus I1 minus I3 omega 1 omega 3. And then the third equation becomes very simple because I1 and I2 are equal, so that term vanishes, and we end up with just I3 omega 3 dot. So this instantly tells us that omega 3 is a constant, and we're going to set that equal to omega naught. So that's just to remind us, anytime I write omega naught, that's a constant factor. So I'll be using that notation throughout everything that we do. So I can return to these equations now and plug that in. So I1 omega 1 dot plus I3 minus I1, and we have omega naught, omega 2. So already we can see that things are simplifying. We've gotten rid of this nonlinear term here. And the next equation is an I1 omega 2 dot plus I1 minus I3, omega 1, omega 3, so that's omega naught, omega 1. So omega 1 and omega 2 are still coupled, but at least the equations now are linear. And so to proceed, we're going to make a little trick where we differentiate one equation and sub it into the second equation.